We are team number 24 discussing on the topic data driven feeder voltage management using association rule mining for distributed solar power voltage systems, which is an extract from IEEE paper feeder solar association discovery using quantitative association rule mining QARM. In modern power grids, renewable energy like rooftop solar has made power flow bidirectional. However, most distribution systems still lack feeder level visibility. Utilities often can't tell which feeder have connected solar panels or how much PV power is injected, leading to voltage instability and operational challenges. Our goal is to address this observability gap through data mining. Our objective is to discover associations between feeder voltages and PV generation using a QARM-based framework. We enhance the traditional a priori algorithm to handle continuous data, allowing us to estimate PV injection levels with statistical confidence and help utilities improve voltage control strategies by translating rules into actionable insights for utilities, and we validate results using IEEE test systems and California real data. Our overall overview of a project consists of two data sets, one from Southern California 28 bus feeder system and National Renewable Energy Laboratory solar power data set. We combine both of these data set and feed it into a Weka tool, and we gain outcome as feeder power voltage association rules for grid stability. The Southern California 28 bus feeder system is about electrical distribution system dataset that model part of Southern California's power grid for research and simulation purposes. The NERL solar power dataset refers to National Renewable Energy Laboratory, who provides solar power data through their laboratory statistics. NERL focused on renewable energy and energy efficiency research in United States. Totally, we combine both of these data sets through a common factor, and we gain in the Southern California bus feeder system provides data about voltage and current magnitude data, and NERL solar power data provides PV generation at 5-minute intervals. After merging, cleaning, and alignment, we obtain a combined data set. Here it is the Southern California 28 bus feeder system dataset, which contains timestamp and the voltage values and magnitude of current, and phase shift also is present. These are the California datasets for National Renewable Energy Laboratory, who provided PV values at different megawatts value, like 13 megawatt, 75 megawatt at 5, each of which at 5-minute intervals, which has values of local time and powers at megawatt. All these datas are combined and grouped together as combined data set, which contains time, day of the year, and voltage values and the corresponding power values in megawatts. This is our system architecture. Data from feeders and PV sources is collected and preprocessed to remove outliers and missing values. The QARM engine then extracts feeder, which is PV relationship. The rule optimization filters out weak rules, and the validated results feed into a situational awareness module where operators can visualize voltage stress and plan corrective actions. The first step in our project is to about data collection. We acquire the raw input data required for analysis, which is already explained. Then we have to pre-process the data which is collected. Now we can see how to pre-process the data using Weka tool. The Weka tool, we can choose the Explorer tab. We can open a file. Now we are considering dataset as CSV files. So I have selected CSV file. Pre-processed data, we have to apply filters. As it is unsupervised data, we are choosing unsupervised data. So I have applied replace missing value filter. After that, I have seen some results. Then I have to discretize all the data set into certain values. I'll set number of bins as 3 and I'm going to discretize all the values. Now I have gained some results. We can visualize all the tabs. Here are some of the tabs you can see, and now we can move on to association rule mining. We selected filtered associated. Now I will edit the a priori options under fields, and I will choose the associated a priori algorithm. I have selected the features as minimum support as 2 percentage and minimum metric as 0.7, and number of rules is restricted to 100. Now we can start the a priori algorithm. I've seen some of the results from the a priori algorithm with some attributes and properties. And these are some of the rules generated, and I have seen some sets of large item sets L1, L2, L3, L4, L5, L6. L1 as 6, L2 as 15, and respectively. I have seen some of the results, and exactly 100 rules are generated, and each rule has its own confidence and lift values. We can inspect all these rules later. Some many rules have been generated with many confidence and lift values. Now we can move on to clustering part. We have chosen simple k-means clustering, and with the number of clusters as a tree, we have started clustering, and we gained outputs of the cluster 0, cluster 1, cluster 2, as we are given number of clusters as 3, with the cluster 0 as 18% and cluster 1 as 18%. Remaining 64% is occupied by cluster 2. We have gained obtained a result of clustering. We have gained output from Weka tool as association rules and cluster outputs. Now we are going to see about situation awareness and output module. It's very important to present useful and explainable results to grid operators from that association rules. It will generate feeder PV correlation tables as like from the association rules provides a confidence value with each estimate. It's about the association situational awareness model diagram. It will transform the validated rules into operator-friendly insights and generate a feeder power voltage mapping tables, heat maps, and visual alerts for voltage stress. The output provides utilities with clear situational awareness for each feeder, including confidence level and graphical dashboards. Now, let us see about the key observations from the QRM results. When PV equal to 3 is which is high, which means to feeder 7 voltage which is low. Is a one of the rule generated, and from that we can when PV output in node 23 is high, feeder 7 tends to experience voltage drops, possible reverse power flow or local overloading. Again, when moderate PV injection leading to mild voltage rise on feeder 12, which is a potential over voltage risk when PV is at node 45 and a feeder is at 12 voltage. Again, it suggests that at when PV is at node 11, it is a high node, and feeder is at 3 kV, 3 amperes current. It suggests increased feeder current during low PV generation, which is normal evening load ramp up. Our main findings are when solar output is high, some feeders show a voltage rise. When solar output drops, feeder experience a voltage fall. When some feeders are more sensitive to solar changes than others, a few feeders remain stable, meaning solar generation doesn't affect them much. These factors helps us to understand what really happening in the grid even without installing expensive new sensors. Through this, we came to a conclusion of our project. And for the problem when utilities cannot easily see which feeder have solar panels or how much power is injected, we can gain solution through this. We use data mining to find relationship between feeder voltages and power generations. These really benefits to improve grid visibility without extra hardware and supports automatic decision making for voltage stability, enables cost effective monitoring for utilities. And some results that we found through this QRM are confidence at 0.33, and we gain lift as less than 1, which is most effective. This PV mitigates feeder load. Thank you.